Every year, thousands of skyscrapers go up worldwide, consuming millions of tons of steel. But what actually keeps a 1,550-foot tower thinner than a pencil standing? Picture a 120-story building with a base just 82 feet wide, a 1:19 ratio. Logic says it should fall. The secret isn't in the glass or the concrete. Just 484 bolts, each costing as much as a car, hold 50,000 tons of weight. How does a small factory in Philadelphia make parts that withstand hurricanes and million-pound loads? And why could one mistake change Manhattan's skyline forever? Stick around, you'll learn what even engineers won't tell you. When I pulled up to the Haydon Bolts factory in Philadelphia's industrial district, I thought I had the wrong place. Small building, regular parking lot, nothing grand. I walked inside, and the first thing that hit me, the smell. Hot oil, superheated metal, ozone from welding. The shop floor held steady at 95 degrees Fahrenheit, even in winter. Workers in safety goggles and heavy gloves moved between machines, each one the size of my garage. Jim met me, the plant's chief engineer. Guy in his mid-50s, voice trained to cut through the roar of a press. "You here to see how we make the bolts for Central Park Tower?" he asked. I nodded. Central Park Tower, a 120-story skyscraper rising 1,550 feet. Tallest residential building in the world. But here's the crazy part. It's narrow. Base is only 82 feet wide. Height to width ratio, 1:19. It's like standing a pencil on end. Any breeze should knock it over. "Why doesn't it fall?" I asked. Jim smiled. "Because of the 484 bolts we're making right now. Each one goes 12 feet deep into the concrete foundation and holds the building's steel frame." He led me to a rack where steel rods lay. "This is where it starts," he said, pointing to a rod 4 inches in diameter and 10 feet long. "This is ASTMA 354 grade BD steel. Tensile strength, 200,000 pounds per square inch. For comparison, regular structural steel has 50,000. I picked up the rod, just to try. It weighed 145 pounds. Stage 1. Heating. The rod gets placed in an induction furnace, where it heats up to 1900 degrees Fahrenheit. At that temperature, the steel glows bright orange, almost white. When the rod reaches the right temperature, a robotic arm pulls it out and transfers it to the forging press. This press is a 50-ton monster capable of generating 1,500 tons of force. One end of the rod gets clamped into a die, and the press strikes it 4 times. Under the press strikes, the metal deforms, forming the hexagonal head of the bolt. Each strike, 250 tons of force. The steel flows into the mold, metal fibers compress, the structure becomes stronger. In 15 seconds, a shapeless rod transforms into a bolt with a head 6 inches across. I see lines running along the metal, like rivers on a map. When you strike metal properly in the right place, the fibers don't tear. They bend, they flow around the shape. That makes the head incredibly strong. Next stage, normalization. The hot bolt cools freely in a special chamber for 8 hours. If you cool it fast, internal stress builds up in the metal, and the bolt could crack under load years down the line. Slow cooling allows stable relaxation. The fibers align themselves in the optimal configuration. Then comes the most interesting part, thread rolling. We walked up to a massive machine that looked like an industrial press. "This is our main weapon," Jim said proudly. Thread rolling machine made by Feta, Germany. Costs $1,002,000. He showed me 2 steel rollers, 18 inches in diameter each. Carved into the roller surfaces were perfect grooves, the negative of the future threads. The bolt gets placed between 2 rollers. They start spinning toward each other at 50 revolutions per minute, creating 50 tons of pressure. Under that pressure, the rollers press into the bolt's surface, deforming the metal and forming the threads. "Why is this better than cutting?" I asked. Jim grabbed 2 bolts, one with rolled threads, the other cut. When you cut threads with a tool, you're slicing through the metal fibers. Look at this cut bolt under a microscope. The fibers are severed. Those are weak points. He pointed to the rolled thread bolt. But here, the fibers don't break. They bend. They follow the thread profile. The metal structure stays intact. Strength increases by 35%, and fatigue strength, the ability to withstand cyclic loads, by 60%. I ran my finger along the threads of the rolled bolt. They were perfectly smooth, without any burrs or irregularities. When the bolts tightened, the threads dig into the nut so hard that loosening is basically impossible. This is critical for skyscrapers. They're constantly getting hammered by wind. Next stage, heat treatment. Bolts go into a furnace and get heated to 1550 degrees Fahrenheit, then rapidly cooled in an oil bath. This is called quenching. The steel becomes exceptionally hard, but brittle. So right after quenching comes tempering. The bolts get heated again, but this time to 600 degrees and fully cooled. This removes the brittleness while keeping the hardness. The result? Perfect balance. The bolt's hard on the outside, but tough enough inside that it won't crack under impact loading. "Now for the moment of truth," Jim said, leading me into the lab. A finished bolt sat mounted on a test stand. Every 5th bolt goes through destructive testing. We take one from the batch and pull it until it breaks. The testing machine, a hydraulic press capable of generating 2 million pounds of force. The bolt gets clamped at both ends, and the press starts pulling. Numbers race across the screen. 100,000 pounds. 200,000. 300. Spec requires the bolt to withstand 1,200,000 pounds, Jim explains. The numbers climb. 800, 900, 1 million, 1 million, 200,000. "Passed," the lab tech calls out, but the press keeps pulling. 1,400,000, 500, 600. Suddenly, a sharp crack. The bolt failed at 1,700,000 pounds. 42% safety margin, Jim says, satisfied. "That's exactly what we need." He showed me the destroyed bolt. The failure didn't happen at the threads. Those are intact. The break is in the bolt's body, and the metal stretched before it snapped. "This is ductile failure," he explains. "The bolt deforms first, warning you about overload, then it breaks. That gives you time to realize something's wrong." We got back to the shop floor, where a finished batch of bolts for Central Park Tower was already laid out. 484 pieces, each 9 feet long, 130 pounds in weight. They were identical. The difference in length didn't exceed a 1/16 of an inch. "How much does one of these bolts cost?" I asked. Jim thought for a moment. "Factoring in material, machining, testing, certification, $32,000. Yeah, that's the price of a budget car." When you're building a 100-story tower that weighs 50,000 tons and sits on a footprint smaller than a basketball court, every single part has to be perfect. Jim tells me about a recent story. In 2012, Hurricane Sandy hit New York. Winds 105 miles per hour. I was standing here thinking about our bolts in 157, the tallest residential skyscraper at the time. 105 miles per hour. That's 8,000 pounds of force per square foot of facade. The building swayed 3 feet from center. 3 feet! In a world where most materials lose their shape and strength under the crushing force of extreme heat, there exists a special stone whose internal structure is hardened to withstand truly hellish temperatures. Molybdenum ore, often found as unassuming gray-blue crystals or embedded in granite massifs, is the source of one of the most refractory metals on the planet. When ordinary iron becomes soft as wax and aluminum turns into a puddle of weak metal, molybdenum maintains its unwavering hardness. This makes it not just a valuable industrial resource, but a strategic component without which the development of aviation, space exploration, and the creation of the most powerful weapon systems is impossible. This metal's journey begins deep in the Earth's crust, where millions of years ago, under colossal pressure, the mineral molybdenite was formed. Molybdenite looks a lot like graphite on the outside. It feels just as greasy to the touch, leaves a mark on paper, and has that distinctive metallic shine. For centuries, people confused it with lead, until 18th century chemists proved that this heavy gray mineral was hiding something new, an element with unique properties. Molybdenum's maximum melting point exceeds 4,700 degrees Fahrenheit. That puts it right up there with heat resistance giants like tungsten and tantalum. But here's the thing. Unlike them, molybdenum is significantly lighter, which makes it the perfect candidate for applications where weight is critical. Mining molybdenum ore is a complex engineering challenge because the concentration of metal in the rock is extremely low. Molybdenum is often just a byproduct when mining copper deposits, but its value runs so high that even tiny percentages make extraction profitable. The process of getting metal from rock starts with massive blasting operations in open pits or deep mines. Huge volumes of ore get crushed into fine sand, which then heads to flotation plants. There, in a water environment with special reagents added, molybdenite particles attach to air bubbles and rise to the surface, forming a concentrate. This grey mass later goes through a roasting stage at high temperatures, where the sulfur burns off, leaving molybdenum oxide. This powder becomes the foundation for producing ferromolybdenum, an iron alloy that's the main component in the metallurgical industry. Every single ton of this concentrate comes from processing thousands of tons of rock. That's how energy intensive and massive this operation really is. Most of the molybdenum mined worldwide goes into creating high-performance alloys. Add even a tiny amount of this element, and it radically transforms the metal's properties. Molybdenum acts like a reinforcement for the crystal lattice, preventing the metal from deforming under extreme heat. This phenomenon allows us to create steels that don't become brittle or flow under load. That's why molybdenum alloys have become indispensable in building gas turbines and jet engines. Inside a combustion chamber, temperatures reach levels that would instantly destroy ordinary structural materials. But molybdenum lets turbine blades operate at the very edge of what's physically possible, delivering massive thrust and rock-solid flight reliability. The weapons sector is another area where molybdenum ore successfully plays a role. The history of using this metal in military affairs began during World War I, when German industry used molybdenum steel to create super-heavy artillery. It turned out that barrels made from this steel could withstand significantly more shots and didn't deform from overheating as quickly as others. Today, molybdenum is a mandatory element in tank armor and armor-piercing shells. Its ability to combine hardness with toughness makes armor plates capable of absorbing impact energy without shattering into fragments. In rocket technology, molybdenum is the choice for manufacturing nozzles and casing elements that come into contact with superheated gases during launch and flight through dense atmospheric layers. Molybdenum alloys show incredible resistance to aggressive chemical environments. That opens doors to petrochemical plants and nuclear power. Pipelines pumping corrosive substances under high pressure, reactors where complex chemical transformations happen. This metal's everywhere, keeping systems running strong for decades. In nuclear reactors, molybdenum's used because it maintains structural stability under constant neutron bombardment, a critical safety factor. This metal fears neither fire, nor acid, nor radiation, making it a true universal tool in the hands of modern engineers. The global molybdenum ore market, highly concentrated. Just a handful of regions control production. China, the US, and Chile are the main suppliers of this resource, and any disruption in their output instantly impacts the cost of high-tech products worldwide. Molybdenum's strategic importance forces major powers to stockpile significant reserves of this metal in case of geopolitical crisis. Exploration for new deposits never stops, because demand for energy-efficient and heat-resistant materials only keeps growing. Take renewable energy development, for instance. It requires molybdenum for next-generation solar panels and wind turbine components that need to survive brutal offshore conditions. The environmental side of molybdenum, or mining and processing, demands serious attention. With extraction involving the movement of massive amounts of earth, companies are forced to implement complex monitoring and reclamation systems. Waste rock dumps and tailings ponds must be reliably sealed to prevent heavy metals from leaching into groundwater. At the same time, molybdenum is highly recyclable. Scrap high-grade steels, spent turbines, and parts from dismantled equipment remain a valuable source of secondary metal, allowing us to reduce the burden on natural ecosystems. A circular economy in this industry isn't just about environmental concerns, it's a path toward lowering production costs down the road. It's fascinating to watch how the journey of metal mirrors the progress of human thought. What was once dismissed as useless soft rock is now the heart of our most sophisticated machines. The transformation of molybdenum into an aircraft engine component. That's a chain of technological victories. Processing through every stage, from that first blast in the quarry to the final polishing of the alloy, demands precision and deep understanding of materials physics. Molybdenum doesn't forgive mistakes. Working with it requires specialized tooling and particular cooling regimes, but the payoff justifies every ounce of effort. This metal is for those situations where reliability is a synonym for survival. The scale of molybdenum use? It's an indicator of a nation's industrial muscle. A country capable of producing and processing these complex alloys automatically enters the upper league of technological players. This drives scientific research in metallurgy, where scientists are pushing to create even more resilient compounds based on molybdenum, adding chromium, nickel, or cobalt into the mix. Molybdenum ore remains one of the resource remnants of our civilization, bridging the planet's geological past and its technological future. It's a symbol of resilience and unwavering strength, a material that lets us operate where scorching gas and destructive chemistry rule. From a humble chunk of molybdenite to a complex turbine blade or armor plate, this metal undergoes a journey of refinement and transformation to become a reliable foundation for human progress. Its story is a tale of how we learned to tame the elements, using gifts from the Earth's depths to create things that seem stronger than nature itself. And as long as humanity keeps searching for ways to work faster, fly higher, and generate more energy, molybdenum will remain that same indispensable element, conquering any inferno in service of our goals. If someone showed you a pile of dull gray rocks and told you your smartphone, electric car, the windmills that generate electricity, and basically all modern technology depend on them, you wouldn't believe it. But it's true. Rare earth elements are the most unremarkable stones on the planet, looking like something way too ordinary. But in reality, they're the most important raw material of the 21st century, over which geopolitical wars are already being fought, and without which we'd still be stuck without the internet and driving gas-powered cars. Let's start with what these things actually are. Rare earth elements are a group of 17 metals in the periodic table. They include lanthanum, cerium, praseodymium, neodymium, samarium, europium, gadolinium, and a dozen other names that sound like spells from a fantasy novel. They're called rare earths, not because they're scarce. Actually, some of them are more abundant in the Earth's crust than copper or lead. The problem is, they never occur in concentrated form. Always scattered, always mixed together. Visually, rare earth ore looks like unattractive gray-brown rock, sometimes with a yellowish or greenish tint. Nothing shiny, nothing bright. If you saw this stuff on the street, you'd think it was just an ordinary rock, or even a chunk of dried clay. Even experts can't always identify valuable ore by sight. You need chemical analysis. This unremarkable-looking rock costs thousands of dollars per ton and determines who becomes the world's technological leader. Rare earth elements have unique magnetic, luminescent, and catalytic properties that can't be replaced by anything else. The most powerful permanent magnets on the planet are made from neodymium, iron, and boron. Without them, there'd be no compact electric motors for EVs, no hard drives in computers, no generators in wind turbines. The phosphors in your phone screen, your TV, your monitor, they contain europium, terbium, yttrium. They're what give you those bright reds, greens, and blues. Your smartphone contains at least 6 different rare earth elements. Neodymium in the vibration motor and speakers, lanthanum in the camera lens, cerium in the polishing materials for glass, yttrium and europium in the display, praseodymium and dysprosium in the magnets. The total weight is just a few grams per phone, but without them, it simply wouldn't work. And right now, over 1 billion smartphones are manufactured every year. Do the math on how many rare earth elements that is. Electric vehicles consume even more. One Tesla Model 3 contains about 1 kilogram of neodymium in its electric motor. That might not seem like much, but when millions of EVs are produced annually, demand becomes massive. Plus, neodymium magnets are irreplaceable. No other material gives you that power-to-size ratio. Try building a compact electric motor without rare earth magnets. You'll end up with a monster the size of a refrigerator. Wind energy is completely dependent on these elements too. A modern 3-megawatt wind turbine generator contains up to 1,300 pounds of neodymium and dysprosium. That's a ton of rare earth magnets per turbine. And tens of thousands of these turbines get installed worldwide every year. Without rare earth elements, green energy simply isn't possible in its current form. Rare earth elements occur in various minerals: monazite, basenacite, xenotime, and others. These minerals contain mixtures of different rare earth elements, along with thorium, uranium, and other radioactive impurities. Useful element content is typically just 2 to 5%. That means from a ton of ore, you only get 40 to 100 pounds of rare earth oxides, which then still need to be separated into individual elements. And that's where the environmental and geopolitical nightmare begins. Mining and processing rare earth ores is one of the dirtiest industrial processes out there. The ore gets crushed, treated with aggressive acids: sulfuric, hydrochloric, nitric. Tons of chemicals are burned through for every ton of ore. Massive volumes of toxic waste pile up: acidic sludge containing heavy metals, radioactive elements, chemical residue. China saw this opportunity before anyone else did. Back in the 90s, when Western countries were shutting down their mines over environmental concerns and sky-high costs, China started mining and processing rare earth elements on a massive scale. They sacrificed ecology for economy. Mining regions turned into toxic wastelands, contaminated rivers, poisoned soil, sickness spreading through local populations. But China gained control of the market. Right now, China produces about 60% of the world's rare earth elements and controls over 80% of their processing. This gives them massive geopolitical power. In 2010, China temporarily banned rare earth exports to Japan during a diplomatic conflict. Japanese high-tech companies panicked. Without supplies, they couldn't manufacture electronics. The world suddenly realized how vulnerable it was to a single supplier nation. Separating rare earth elements from each other is a whole separate pain. They're so chemically similar that separating them using classical methods is nearly impossible. They use multi-stage solvent extraction or ion exchange chromatography, basically processes that require hundreds of repeated cycles. At a plant with thousands of tanks, solutions get pumped back and forth for weeks until finally individual pure elements emerge. For example, to get pure europium, the element that gives red color in screens, you need to run the solution through dozens of purification stages. Europium makes up only a tiny fraction of the total rare earth element mixture, so a kilogram of pure europium can cost thousands of dollars. And then it's added to phosphors literally in milligrams for each screen. Neodymium magnets. That's a separate success story. They were invented in the 1980s simultaneously in the US and Japan. These magnets are 10 times more powerful than ordinary ferrite ones. They made a revolution in miniaturization possible, shrinking the size of motors, speakers, generators by several times. Apple AirPods fit right in your ear and still deliver decent sound, thanks to tiny neodymium magnets inside. Making neodymium magnets is complex too. First, they melt an alloy of neodymium, iron, and boron. Then they pulverize this alloy into a powder just a few micrometers in size. The powder gets pressed into molds under a magnetic field to align the crystal structure in the right direction. It's sintered in a vacuum, or inert atmosphere, further processed to enhance its properties. Only then do you get a finished magnet. The problem with neodymium magnets, they lose their magnetic properties when heated, depending on the alloy. For applications where temperatures run higher, like in electric vehicle motors or industrial engines, they add dysprosium or terbium. These elements boost the operating temperature, but they're even rarer and pricier than neodymium. Catalytic converters in cars, another critical application. Every gasoline-powered vehicle has a catalytic converter containing cerium, lanthanum, and other rare earth elements alongside platinum and palladium. They transform toxic emissions into less harmful substances. Without them, modern environmental standards are impossible to meet. And again, 1 billion cars worldwide, each needing these elements. Right now, the US, Europe, and Australia are trying to revive their own rare earth mining to reduce dependence on China. New mines are opening, processing plants are being built, but it's a slow process that'll take years. China has the advantage in experience, infrastructure, and willingness to tolerate environmental consequences. The competition is tough. There are also efforts to recycle rare earth elements from electronic waste. Old hard drives, smartphones, electric motors contain these valuable materials. But the extraction process is complex and expensive. You have to disassemble the device, separate components with magnets or phosphors, dissolve them, purify them. Economically, this is often unprofitable compared to mining new ore. Researchers are working on alternatives. They're trying to create magnets without rare earth elements, using iron, cobalt, manganese. So far the results are promising, but we're a long way from industrial scale. Phosphors are also being replaced. Quantum dot LEDs promise bright colors without europium and terbium. But mass adoption will take decades. Here's a wild fact. Some rare earth elements don't even have real uses. Promethium is radioactive and doesn't occur naturally at all. It's made artificially in nuclear reactors. And applications? Minimal. Lutetium and thulium are the rarest of the bunch, with super niche uses, mostly in science and medical research. Rare earth prices are crazy volatile. When China restricted exports in the 2010s, prices shot up dozens of times over. A kilogram of neodymium oxide cost over $500 instead of the usual $50. Companies panicked, scrambled for alternatives, tried cutting consumption. Then China ramped up supply again, prices crashed, and tons of new mining projects went broke and shut down. The future of rare earth elements is tied to the development of green technologies. Electric vehicles, wind energy, solar panels, energy storage systems, all of this demands more and more of these elements. Forecasts say demand will grow 3 to 5 times by 2030. It's a massive challenge for the industry. Where do you find that much? How do you process it without destroying the environment? How do you avoid depending on a single country? Picture this paradox. How do you cut something harder than any steel? Super hard materials like industrial diamonds or tungsten carbide slice through metal, grind glass, shape airplane turbine blades, and even protect your smartphone screens from scratches. But how do you machine them? It's a hidden science where water pressurized to millions of pounds per square inch, lasers that vaporize atoms, and diamond tools overcome hardness measured 10 times greater than steel. Let's crack this engineering paradox, from labs to factories where the key components of our modern world are born. Industrial diamonds, the hardest natural material on Earth, with a hardness of 10 on the Mohs scale. Tungsten carbide isn't far behind. Its hardness ranges from 1600 to 2200 on the Vickers scale, making it ideal for drill bits, mills, and turbine inserts. These materials withstand temperatures over 2800 degrees Fahrenheit and pressures of hundreds of tons per square inch. But their hardness is also a curse. Ordinary tools shatter against them like glass on rock. So engineers invented special methods: water jet cutting, laser ablation, and precision grinding. Each one's a hack that bypasses the limits of physics. Water jet cutting. It's high pressure magic. Water under 60,000 psi pressure shoots through a sapphire or diamond nozzle less than 0.02 of an inch in diameter. The jet reaches speeds of 3,000 feet per second, packing enough energy to slice through an 8-inch sheet of tungsten carbide in minutes. For ultra-hard materials, they add an abrasive, garnet, or silicon carbide. The grains accelerate to supersonic speeds and blast away particles of material. No heat, no warping or heat-affected zones, which is critical for turbine blades. Accuracy down to 1,000th of an inch over 10 feet, zero tool wear. When regular water with abrasive can't cut it, say for microscopic holes or perfectly clean edges, lasers enter the arena. Laser ablation works like this. Ultra-short laser pulses hit the material with such force that atoms just fly off, like a shockwave. No melting, no cracks, just clean vanishing, layer by layer. The pulse lasts 1/10 of a second, faster than you can blink. Each flash carries 1 to 10 microjoules of energy onto a tiny spot the size of a micron. In tungsten carbide or diamond, this creates miniature plasma, a hot ionic cloud that rips atoms away. The wavelength of 1030 nanometers in the infrared spectrum penetrates exactly 1/10 of a micron deep and removes an ultra-thin layer with 1 micron precision. The result? Perfectly smooth edges without burrs. In industry, this is done on machines from Coherent or Trumpf. They cut jewelry-grade diamonds for a $50,000 ring, or lab-grown diamonds for semiconductor chips. The process runs cold. The surface heats to a maximum of 100 degrees Fahrenheit, so there's no deformation or material stress. The speed's modest. For diamond, we're talking 1 cubic millimeter per minute, but the precision is surgical. The price tag bites hard. $500,000 for the laser, but it pays for itself in microelectronics. A single iPhone chipset requires processing diamond substrates, where the laser cuts microchannels just 10 microns wide. Without it, you're dead in the water. Here's a cool fact. In 2024, NASA used this tech on Mars rovers. They shaped carbide nozzle parts and heat shields that can take 3,000 degrees without warping. The laser punched thousands of microholes for cooling, 0 defects. Why's that cool? A regular laser melts edges 50 microns deep, creating a brittle zone. But the femtosecond laser, it's like a surgeon. Energy goes straight to breaking atomic bonds, and heat dissipates instantly. For turbine blades or smartphone screens, this is perfection. The surface comes out mirror smooth. Your phone drops, but glass with CVD diamond coating doesn't scratch. And behind that gleam, a laser that vaporized microns of super hard metal. These aren't just machines. These are genius hacks breaking the impossible. Check it out. Water jet plus laser in one machine. Water roughly cuts through 8-inch carbide. Then a femtolaser finishes microns with insane precision. Hybrid monsters tear through thick turbine blanks for SpaceX, where conventional methods fail in seconds. And there's the brain of the future. Artificial intelligence analyzes every micron, optimizes trajectories, and slashes defects by 40%. Instead of tons of scrap metal, perfect turbine blades spinning at 100,000 RPM without vibration. The global superhard materials processing market hits $15 billion in 2025. That's explosive growth at 8% annually. This surge is driven by key technologies of the future. 5G antennas with diamond coatings that withstand millions of cycles without wear, Tesla electric car batteries with carbide components for maximum energy efficiency, SpaceX Starship nozzles that burn at 5,400 degrees Fahrenheit in the hell of atmospheric re-entry. Every General Electric turbine spinning at 120,000 RPM. Every Samsung screen with Gorilla Glass. These are fruits of a secret science where water cuts diamond. Lasers vaporize tungsten carbide, and vibrations shatter the unbreakable. The market's booming thanks to demand for ultra-precise parts, gigafactories, Starlink satellites, medical instruments. By 2030, it's projected to hit $32 billion, turning engineering paradoxes into mass production. Every component, from microchips to rockets, carries the fingerprint of this hidden craftsmanship. I can already see a flood of comments like, "Why does this matter beyond smartphones and space?" Heads up, these technologies are crucial even for your health. Tungsten carbide is a hardness monster, but when you try to cut it mechanically, tools shatter in minutes. Electrochemical etching is the hack. Instead of breaking tools, the electrolyte eats the binder, the cobalt, and the tungsten just falls away. The result? A perfectly clean surface. No burrs, no cracks, no heat buildup. And this method has serious real-world value in medical instruments. Surgical cutters for spine and joint procedures. Bacteria can't stick to these surfaces. Surgeons cut through bone cleanly, without microscopic tissue explosions. Sandvik makes endodontic files for dentists, tools that navigate root canals. A regular cutter would snap inside the canal, but these files can twist through 5,000 cycles without breaking. Instead of hammering away, electrochemistry. Turbines fly longer, surgeries get safer, tools last weeks instead of hours. Sounds amazing, but what about emissions, water consumption, energy use? Let's break it down honestly, where the eco-heroes are and where the gray zones hide. Water jet cutting, the king of green. Water is the main weapon. 99% of it recirculates in a closed loop. Garnet abrasive? Natural mineral, non-toxic, gets reused up to 10 cycles. Energy, 30 to 50 kilowatts per hour, less than laser. But here's the catch. Old machines dump dirty water into sewers with metal dust. Modern flow, or OMAX, filters are almost 100%, zero discharge. Fact, Boeing cut chemical waste by 70% with water jet versus electrical discharge machining with oils. Verdict, green if you've got filtration. Laser ablation, energy vampire, but cold. Femtosecond lasers devour 5 to 20 kilowatts per hour. Lasers, up to 50 kilowatts. Electricity equals emissions unless you're running solar panels. But the upside, zero abrasive, zero water, zero chemicals. There's practically no SAW. The material vaporizes into gas. For microelectronics, it's ideal. Processes diamonds without waste. Verdict, moderate but clean process. Diamond grinding, the dirty leader. Diamond wheels plus emulsions equals tons of abrasive paste with carbide and oils. Every liter of lubricant, a petroleum product, goes into hazardous waste. But there's progress. Minimal lubrication, drops instead of flow, 90% reduction. Cryogenic cooling, no fluids at all. Verdict, dirty but reforming. Every hour, millions of metal parts are born around the world that have never seen the inside of a smelting furnace. They're not cast, not machined from bar stock, and not forged with a hammer. So what is this metal that starts out looking like powder, then goes on to withstand the loads of a jet engine? Powder metallurgy, a quiet technology working behind the scenes of the modern world. In your smartphone, your car, hospitals, and even in space. It saves up to 70% of material, creates shapes impossible for traditional manufacturing, and changes the very logic of metal itself. But there's one moment almost nobody talks about. The process where the metal isn't solid yet and is no longer powder. Stick around to the end, and you'll find out why it's precisely in this phase that the fate of strength, lifespan, and cost of the future part is decided. From the gears in your phone to jet engine parts, from surgical instruments doctors use in operations to car components, powder metallurgy is everywhere. It's a technology few people hear about, But without it, the modern world would look completely different. Let's break down how it works and why it's so awesome. Start at the very beginning. Metal powder. These are specially manufactured particles ranging from 1 to 100 micrometers in size. For comparison, a human hair is about 70 micrometers thick, meaning these particles are so tiny that if you pour them into your palm, they feel like velvet or face powder. Under a microscope, each particle looks like a tiny sphere or an irregular shape with a smooth surface. There are several ways to make this powder. The most popular? Atomizing molten metal. A stream of liquid metal at temperatures around 3000 degrees Fahrenheit gets blasted under enormous pressure by jets of water or gas. The metal instantly shatters into millions of tiny droplets that freeze in mid-air as they fall. What you get is a fine powder with particles that are almost perfectly spherical. Another method? Electrolysis. Metal deposits from a solution onto electrodes as fine particles, which are then collected and dried. This method produces very pure powder, but it's pricier. Then there's mechanical grinding in ball mills, where metal is simply pounded by heavy balls until it turns into powder. But these particles come out irregular with sharp edges, which isn't always ideal for further processing. Each metal needs its own approach. Iron, stainless steel, copper, aluminum, titanium, tungsten. They all become powder differently. You can also mix powders from different metals to create alloys with unique properties that are difficult or impossible to achieve using traditional methods. Now here's where it gets interesting. What do you do with this powder? Step 1. Mixing and prep. You add various substances to the metal powder. Lubricants so the particles slide past each other more easily, binding agents that hold them together, sometimes graphite or other additives to improve properties. All of this gets thoroughly mixed in special mixers, so every single particle is coated with the right additives. Next comes pressing. The prepared mixture gets poured into a mold called a die. This die is made from super hard steel and has the exact geometry of the final part. Powerful presses squeeze the powder from above and below, creating pressure from 15 to 60 tons per square inch. That's like stacking several elephants on an area the size of your fingernail. Under that pressure, the powder particles compress, deform, and lock together mechanically. The air between them escapes, and the powder transforms into a dense blank that actually holds its shape. This is called a green compact, or green body, though it has nothing to do with color. Just the term. It's still pretty fragile and crumbles easily if you're not careful, because the particles are only held together by mechanical interlocking and adhesive additives. The green compacts get loaded into special furnaces, where they're heated to temperatures ranging from 1600 to 2300 degrees Fahrenheit, depending on the metal. That's below the metal's melting point, but hot enough to get the atoms moving and diffusing between particles. Something remarkable happens inside that furnace. Metal atoms on the particle surfaces start migrating, jumping from one particle to another, filling voids, creating strong metallurgical bonds. The boundaries between individual particles gradually dissolve, and the powder transforms into a solid, monolithic material. The part shrinks, becomes denser. It can lose up to 20% of its volume. The entire sintering process takes several hours and happens in a controlled atmosphere. Typically, you use inert gases like nitrogen or argon, or even hydrogen, to prevent the metal from oxidizing at high temperatures. If you allow contact with oxygen, the part will develop an oxide film and lose its strength. After sintering, the part is cooled slowly. Cooling it too fast can create internal stresses and cracks. And here's where the final magic happens. The part acquires its ultimate properties. The metal's microstructure forms, grains grow, internal stresses are relieved. What do you end up with? A part with a density of around 90 to 95% of cast metal. That means there are still some pores inside, tiny voids just a few micrometers in size. But this isn't a flaw, and sometimes it's actually an advantage. These pores can hold lubricant, making the part self-lubricating or absorb vibrations and sound. These parts are often stronger than cast equivalents. Why? because the microstructure turns out fine-grained and uniform. No large crystals that could be weak spots. No segregation or inconsistencies that happen during casting. The metal is distributed evenly, and impurities, if any, are also distributed perfectly. For some applications, you need maximum density with zero porosity. That's when additional processes come in. Hot isostatic pressing. The part is reheated and compressed with gas under pressure up to 10 tons per square inch from all sides simultaneously. Pores collapse, and density reaches nearly 100%. Or you can use powder forging. The sintered blank is heated and forged, just like regular metal. You end up with a part that has properties impossible to achieve any other way. Super strong, ultra dense, with precise dimensions. The beauty of powder metallurgy is that you can make complex shaped parts with virtually zero waste. With traditional machining, you cut the desired shape out of a metal block, and up to 70% of the material ends up as chips. Here, the powder is poured precisely into the mold of the future part, sintered, and that's it, minimal scrap. After sintering, parts often require minimal additional machining or none at all. Dimensions hold to within a few hundredths of a millimeter. For comparison, a sheet of paper is about 100 micrometers thick, and powder part precision can be 10 times better. You can create gradient materials, where different parts of a single component have different compositions and properties. For example, a gear where the teeth are made from hard, wear-resistant alloy, while the core is made from softer, tougher metal that won't break under load. You can't do this with casting or machining. Powder metallurgy lets you work with metals that are tough to process traditionally. Tungsten melts at over 6,000 degrees Fahrenheit. Try casting that in a regular furnace. But with powder, you can easily make tungsten contacts for electronics or crucibles for melting other metals. Titanium. Strong as steel, light as aluminum, but incredibly expensive to machine because it's chemically reactive and abrasive. Powder metallurgy makes titanium parts economically viable. That's why it's used for medical implants, artificial joints, dental implants, bone plates. In the automotive industry, powder metallurgy is the standard for gears, bearings, piston rings, valves. A single modern car contains up to 110 pounds of parts made by this method. They're cheaper, lighter, and more reliable than traditional ones. In aerospace, powders are used to make turbine blades that withstand temperatures over 3,600 degrees Fahrenheit and spin at over 10,000 revolutions per minute. Composite materials from particles of different metals and ceramics deliver properties impossible for conventional alloys. 3D metal printing is exploding right now. It's basically powder metallurgy, but instead of pressing, you lay down thin layers of powder and fuse them with a laser or electron beam, one layer at a time. You can create parts so complex, they're impossible to make any other way. Hollow structures, internal channels, lattice frameworks. Can metal burn brighter than the sun? Sounds impossible, but one element does this every day. And we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside. Yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. Every year, the world melts down more than 16 million tons of silicon metal, a material without which modern civilization would simply grind to a halt. It makes steel stronger, aluminum lighter, and solar panels possible. But here's something almost nobody knows. To create just 1 ton of this metal, furnaces operate at temperatures exceeding 5,400 degrees Fahrenheit and consume as much electricity as hundreds of American households use in a month. So why does this silent giant hide a diamond structure inside? And what discovery about silicon will change your understanding of technology if you stick around till the end? Industries use metallurgical-grade silicon as a foundational material for creating ferroalloys, particularly ferrosilicon, which gets added to steel to improve its strength, corrosion resistance, and ability to withstand high temperatures. How steel deforms, its elasticity, and behavior under load largely depend on how silicon dissolved in the metal matrix behaves. Metallurgical silicon is also critical for producing aluminum alloys, where it's responsible for reducing weight and improving the alloy's ability to maintain its shape when heated. For example, in cast aluminum parts for automobiles, the silicon content can reach anywhere from 12 to 14% by weight. Another key application is obtaining purer silicon suitable for electronics and photovoltaics. Metallurgical-grade silicon serves as the starting point for producing polysilicon, which gets purified to impurity levels in the parts per billion range. This ultra-pure material is what they use to form ingots and wafers for microchips and solar panels. Demand in this sector has shot up dramatically in the US over recent decades, driven by renewable energy expansion and the needs of data centers. To put the scale in perspective, manufacturing a single solar panel module that's about 11 square feet requires roughly 6 or 7 pounds of silicon in the form of high-purity polycrystalline material. Metallurgical-grade silicon has additional applications too. It's used in chemical manufacturing to synthesize silicones, which are needed for sealants, lubricants, medical devices, household products, and electrical insulation components. It serves as the starting material for silanes, compounds that act as coupling agents between organic and inorganic materials, ensuring stronger surface bonding in composites. Certain types of silanes are used as part of adhesives and coatings that help extend the service life of structures in humid or corrosive environments. Technological progress constantly raises the bar for metallurgical-grade silicon, since purity, grain size, and consistency of properties directly impact the quality of the final product. In American industry, research continues on optimizing electric arc furnaces to cut energy consumption, as well as on utilizing carbon monoxide byproducts. On top of that, companies are developing ways to recycle silicon production waste to bring part of the material back into the cycle and reduce emissions tied to mining fresh quartz. All of this makes metallurgical-grade silicon one of the foundational industrial materials. Without it, modern electronics, transportation, and energy sectors couldn't keep up their current pace of development. To turn mineral oxide into metal, you need extremely high temperatures and a carefully controlled reduction reaction. This is done in large electric arc furnaces that operate at massive temperatures and consume enormous amounts of electricity. The furnace is loaded with crushed quartz along with carbon-based reducing agents. Most commonly, these are charcoal, coke, or various carbon briquettes, selected to ensure stable combustion and the right reactivity. Powerful graphite electrodes create an arc that heats the center of the furnace to approximately 5,430 degrees Fahrenheit. Under these conditions, ordinary rocks transform into active participants in the reaction. Silicon dioxide reacts with carbon, and as a result, oxygen is removed from the oxide. Gaseous carbon monoxide forms, while pure silicon transitions into a liquid state. The molten material is heavier than the surrounding charge, so it slowly settles to the bottom of the furnace, accumulating as a metallic mass. Once enough silicon is collected, it's released into special crucibles or troughs. As it cools down, the liquid metal solidifies into solid ingots, which are then crushed into smaller pieces that are easier to transport and process further. At this stage, it's crucial to maintain conditions that prevent impurities from oxidizing again or mixing with the cooled silicon. The raw material obtained at this point already has commercial purity of around 99%. This level of purity works fine for ferroalloys, but it's not enough for more demanding applications. Next comes the stage of refining the metal to higher purity. Silicon can be remelted in a vacuum or under an inert atmosphere, using various methods like sorption, zone melting, or chemical purification. The main goal here is to get rid of impurities like iron, aluminum, calcium, and sometimes phosphorus and boron. The impurity content is controlled with precision down to parts per million, because even a tiny amount of foreign elements can seriously affect the electrical properties of the final product. After purification, you get metallic silicon with the characteristics needed to produce alloys, silicones, or even purer polysilicon. The production process itself is energy intensive, so it's critical that the method ensures minimal heat loss and makes the most efficient use of electrical power. Modern furnaces come equipped with heat recovery systems and electrode feed control. This helps cut down overall energy consumption and boost productivity. Process optimization is a big deal here, because on average, making 1 ton of metallic silicon requires about as much electricity as several hundred American households use in a month. The quality of quartz sand plays a crucial role too. The purer the initial silicon dioxide, the fewer purification stages are needed after melting. Quartz with high impurity content can lead to increased energy consumption and greater furnace wear. That's why deposits supplying raw materials for the silicon industry must meet strict standards for chemical purity and mechanical uniformity of the material. Silicon, though it doesn't have gold's shine, is a true geochemical giant, an absolutely irreplaceable element. In terms of abundance in Earth's crust, it holds an honorable second place, losing only to a non-metal, oxygen. This means that, essentially, we live on a massive silicon-oxygen planet. It's hard to wrap your head around this, but this substance makes up a colossal 27.6% of our planetary crust's mass. Just imagine, almost every fourth ton of material we see beneath our feet is silicon or its compounds. It forms the backbone of entire mountain ranges and serves as the building material for countless minerals called silicates. This element isn't just filler, it's the foundation of our entire modern civilization. As a semiconductor, it powers every chip, processor, and transistor inside your phone, computer, and car. Silicon is the gray eminence of our planet and our technological age. Quiet, abundant, but absolutely omnipotent. Its extraordinary purity is essential for microelectronics, making it one of the most demanding materials in the world. If you pick up any rock or handful of sand, you're holding an entire silicon factory. We all live on a massive silicon planet, not just a water one. Silicon could have been super expensive and sparkly, but it chose the humble path of being a semiconductor to run all the world's electronics instead. Why am I saying this? Because pure silicon has the exact same crystal structure as diamond. To put it simply, why silicon with the same structure as diamond isn't actually a diamond comes down to two key differences: atom size and bond strength. Diamond is made of carbon atoms, while silicon is made of silicon atoms. Plus, a carbon atom is tiny, whereas a silicon atom is much bigger. Even though both elements form the same spatial lattice, silicon atoms, being larger, force the whole structure to expand. This makes the bonds between them longer and, as a result, weaker,